Hi everyone. I'm Yuchen Lin. You can also call me Jason. Today I'm talking about my dissertation proposal: information recovery in online social networks, identification and localization. My research focused on Facebook public pages. Among the online social network data, um, Facebook page, public page, for example, like we can see in the last figure, is a Golden State Warrior fan page. Um, it was mainly used as public figures by local business, companies, organization, or public figures like musicians, politicians. Um, Hosts can choose to like other pages. The likes functions as promoting other pages to the users, namely the community participants. So this formulates a page information page graph. For example, Golden State Warriors can like Sport Illustrated, Oakland Museum, or Giving Tuesday. And the page information include page ID, name, category. It's a sports team of for Golden State Warriors. Country, fin count, description. So my research scope is based on public page graph and can be extended to organization relations, information recovery, and also page property. For information recovery, um, there's attribute identification for missing data, privacy preservation, and also for security, adversarial manipulation detection. For page property, there's global page detection. Also, we can work on page lifecycle analysis. So my current work is focused on attribute identification and also global page detection. So specifically, my research questions um, among the various information, local attributes are of particular interest to social scientists. So these digital footprints give since these digital footprints give social scientists insight into users' physical footprints outside of OS and online social network. So my I try to approach and explore these research questions. First, how to identify missing nationality information of pages. Second, what challenge will we face when the identification becomes fine-grained? Like, how do we identify subdivision, like state labeling of pages? Third, how do we differentiate local pages from global pages? There are some related work. First, Facebook user graph on Uganda, they do the analysis on the friendship graph and by categorize its global structure and related network properties of user friendship graph. Um, Professor Barnett in 2017, they examined international relations among countries by building connections from concurrence of country keywords in Facebook users' posts. And one used the keyword linguistic inquiry and word count to show that each page has its own characteristic, especially framing exists in political and news pages. However, these these previous works do not leverage a relationship among public pages to analyze cross-page user behaviors. The other direction of related work is user geographic location, geolocation prediction. First, they use content-based keyword analysis, takes advantage of text messages related to a strong local geoscope. There are many previous work on this. Also, they use social ties, like friendship, relationship between users. The last part, also the latest one, they use cluster analysis. It gets decent results in various region granularities. Actually, they compare geometrical mean, k-means clustering, DB-scan, and Gaussian mixture models. But most of these works, the mainstream they use user location by leveraging the tweet text information. In um, So for my following lecture for the following I would after introduction I would talk about the identification of pages nationality, also how do we provide in Facebook public page graph, then the subregion identification of pages, also next is the global page detection, last is my future work, it's my outline. So our question is why are nationality information missing? The reason is because page hosts can choose not to uncover geographical location of a page. In our data, there are 8 million pages. 49.76% out of 60 million pages show their country info. Thus, we propose an algorithm to identify country information. Since the majority of public pages are commercial in nature, they tend to use more accurate location data. In comparison, users do not have this kind of motivation to provide accurate location data. Thus, we use direct collection to obtain golden location data on Facebook. For the data collection part, we use Facebook Graph API to collect it, version 2.8 to collect it. Our strategy is snowball sampling, starting from a set of public pages, a seed, and then in the process of crawling, we expand this seed by adding more pages into lists, which are liked by the listed pages. So our problem here is given a public page graph with some missing attributes, how do we identify the missing nationality attributes of these pages? For example, there are two missing attributes for these two question mark pages. So the first algorithm we propose is the majority vote algorithm. The vertices are known country and unknown country pages. Edges are like connections. We take it as undirected. Observation. Most neighbors come from same country, so our concept is use majority vote by neighbor's nationality. Our implementation use a priority queue by known number of known country neighbors. Thus, the time complexity is E plus log B, space complexity is E plus B. So for the performance of accuracy, the accuracy is 90% with 50% unknown country pages. This percentage is to simulate the same distribution as the data we crawl. Also, our F1 score is 0.904, which is computed by prediction and recall. The processing order is by number of known country neighbors. The accuracy remains over 90% when a page has at least 30 known country neighbors. To test the robustness, we changed the unknown country page ratio among all pages, and we found that the accuracy is still over 90% when the unknown ratio is less than 60%, and the standard deviation is smaller than 0.15%. The next part I would talk about how we profile Facebook public page graph. There are several subsections in this section. First, I'll talk about the page distribution, then the connectivity, then the country international impact from these 3 perspectives, social influence, correlation, and also clustering. For the page distribution by country, we can see among the 60 million pages, 41% are US pages. The second highest is the orange part, 5.5% United Kingdom. And we can see the top 10 countries occupy nearly 70% of pages. This reflects Pareto principle. For the category, if we see the distribution by category, there are actually over 1,000 categories in total in Facebook. Also, the Pareto principle also apply here. the top 100 category covers 91.5%. Thus, we classify the top 100 into 7 broader categories, namely the brands and products, people, company, and organizations, website and blogs, entertainment and local business and businesses. We can see the sum of companies and organizations and local business and places accounts for over 60% of all pages. In the bottom figure, um, country pages are sorted by percentage of companies and organizations. We can see that companies and organizations and local business and places are major parts in most countries, and they occupy the similar percentage. And this again supports the argument that most Facebook pages are commercial promotion oriented. For connectivity, the average degree is 62, median is 17, and 77% of domestic ages means most ages are between pages in the same country. We run breadth research from the highest degree page in every country, and we found that in this heat map, the yellow dots are within 5%, and most are green dots. So we found that most are within 5% in breadth first search. For the international graph, page graph, we define as vertex and ages. Vertexes are aggregating by public pages whose nationality are the same country. The ages are a set of directed ages denoting source nations like the destination nations. To address the country's international impact, we use two measures: PageRank and Botunian centrality. Botunian's centrality, PageRank analyzes the relative importance of a vertex in a graph by calculating the probability that a vertex would be reached when starting from a random vertex. The algorithm assigns an initial probability value to each vertex. And there are two parts, 1 minus d and also d, to probability part. And the first part is 1 over n, that's the average probability. The other part is computed by the neighboring vertex. Vj. Bvj is a set of vertex which like Vi, and the value is Pvj over Lvj. Lvj is the number of likes from vertex Vj. And it keeps iterative updates probability value of each vertex. Botunian centrality finds information hubs in the network graph. It measures number of shortest paths which pass the least vertex. The higher the Botunian centrality means the more information will pass through that vertex by connection of edges. The higher the Botunian centrality means it would have higher potential to disconnect graph if it got removed. So here we treat PageRank and Botunian centrality as a form of social influence. So we see the country international impact from a social influence perspective. And yeah, there are 242 vertices countries in this international graph. And this table shows the union of top 10 PageRank and Botunian centrality countries in this order by PageRank. So the column of number of nations connected represents average number of in degree and out degrees ages which connect two nations. Not surprisingly, we can see that the United States and United Kingdom they have the highest PageRank and also the Botunian centrality. However, the interesting part is that both New Zealand and Switzerland they have great influence as well, but they actually have just 86,000 pages and also 30,000 pages, which is quite small. which are quite small compared to the other top 10 nations. This implies that these two nations utilize Facebook public pages efficiently to connect with other pages internationally, which would benefit promoting their own nations and interacting with other nations. In this analysis, in this table, there are 8 countries overlap in the top 10 list of both PageRank and Botini's centrality, but we actually have some underestimations due to the low involvement in Facebook. For example, in the right figure, the red part is China, brown part is Vikantate. China authority forbids Facebook, and most Chinese will use Weixin, WeChat, or QQ instead. Vikantate VK is much more popular in Russia than Facebook. For the correlation, if we see the country impact from the correlation aspect, we use Kendall's rank correlation coefficient to examine the correlation among the rank list of attributes, to examine the correlation among attributes of vertices in this graph. Kendall's rank correlation coefficient talk is defined by NC and ND. NC is a concordant pair, ND is a number of discordant pairs. If xi smaller than yi and xj also smaller than yj, then it's a concordant pair. So it's 1 if two rank lists are the same, and -1 if they are reversed, 0 if it's independent. From this table, we can see highest is a PageRank between PageRank and number of nations connected. So this tells us countries connected to more nations have higher impact. Also, the increasing number of nations connected results in higher social influence in Botini's. But we can see the Botini's and number of pages is just 0.795, which means the number of pages does not necessarily guarantee a more important information hub. Next, we see the relationship from clustering. Countries' international relationship from clustering. Clustering is applied to find community structure. Modularity function is proposed by Newman. The Q is the fraction of within community ages minus expected value of this fraction if ages were distributed at random. Ki equals the summation. Ki is the age weight between vertex. Ki is the sum of the weights of the ages connected to vertex I. So Aij is the actual number of ages between I and j. Ki times kj over 2m is the expected number of ages between I and j if it's distributed at random. And Ci is the community assigned to vertex I. So delta Cij is 1. If Ci equals Cj, means these two vertices are in the same community. This modularity value is positive if the number of ages within groups exceed number of numbers expected on the basis of chains. So for a given division of networks, vertex into some modules, modularity reflects concentration of ages within modules compared with random distribution of links between all nodes, regardless of modules. However, this modularity function cannot scale up to large networks because it's NP-hard. For clustering, thus we apply a two-phase unsupervised fast algorithm to calculate it. This is proposed by Blondel. This algorithm is not only fast but also unsupervised, means that we don't have to have a predetermined fixed number. Our results show that there are three groups, primary two groups. There are three groups and primary two groups. The red dots consisting of Western nations, United States and United Kingdom, and green dots consisting of Islamic countries. Most use Arabic languages. So this phenomenon supports Huntington's arguments. First, white civilization will clash. Second, the West versus the rest. First, the civilization are differentiated from each other by history, language, culture, tradition, and most important, religion. And though technology makes world smaller place, difference among civilization are too basic that it cannot be seen. And also, the West versus the rest, um, the bandwagon effect shows here that companies can attempt to join the West and accept its values and institutions. So we can see that most other countries join the West as the red dots. The next part I will talk about subregion identification of pages. There are in this section I will first talk about motivation and problem statement, then challenges, and the algorithm we propose, and last the data set and experimental results. Motivation, fine-grained attribute identification will facilitate information precision, which is useful for marketing, advertising, and regional social research. So what are the challenges when dealing with fine-grained attribute identifications? And problem statement is that how can we accurately identify state labeling of pages in the US? So our first thought is to apply majority vote algorithm. Location here is designated as state information in this scenario. The location labeling is determined by the most votes. Here our accuracy is only 59.4% for the state labeling. We randomly select 50% as known pages, as unknown pages. This algorithm actually, however, this algorithm works well in page nationality prediction, which is 90% accuracy. So we think about what are the challenges. So the following challenges could contribute to a low accuracy when the majority vote algorithm is applied. First, different countries may speak distinct languages, but this does not apply to the states. One public page is less likely to follow another public page, which uses a different language. Communication among countries is much less than communication among subdivision regions, which are domestic. Means the interaction between states are more complex. In addition, states in US are much closer to each other compared to countries, so they have shared culture, language, and proximity. So we propose our baseline algorithm. We utilize locality of states to find pages belonging to their corresponding states. So our first thing is to pick out anchor pages with local property as multiple seeds to start preferred search from. Our target classifier have 51 classes, 50 classes of US states, and a class of other regions or other countries. And we propose a state distance vector SDV as composed of IHOP and also OHOP. IHOP denotes the hop distance between this page and the CSI with using the inward edges as connection for breadth search. So for the anchor page selection, our algorithm's effectiveness highly depends on the anchor page selection. So these pages have to be as local as possible such that the SDV can provide authentic tendency of a page's locality. For example, what are the suitable cases? The suitable cases are those pages focusing on local communities, like state university, government, park, or police organizations. Those pages, they are not suitable are those popular and thus may have a global impact, like NBA fan page, like Golden State Warriors, MLB, NFL sports teams. So here in our experiment, we adopt all subsidiary pages of onlyinYourState.com as a set of anchor pages. It has a distinct page for each state. Each subsidiary page mostly connects local communities. Um, in particular, because California is much larger than other states in perspective of population and economy, onlyinyourstates.com splits California into southern and northern parts. So we use these two pages as our anchor seeds as well. So there are actually 51 anchor seeds. In addition, since only in Idaho had been registered, they use the website use Idaho only instead. For the advanced algorithm, we utilize we found that um, we found that the baseline algorithm has some drawback because a local page can have a few connection with those page far beyond the state where it resides. Like somehow it connects to some middle pages, or it just have connection with the anchor seeds. So this kind of connection noise would highly reduce prediction accuracy. Thus, we propose state neighborhood probability (SNP), which is composed of INP and also ONP. Um, this probability INP denotes inward neighborhood location probability between this page and the adjacent pages belonging to region RI. So it is defined as the inward edges over the sum of inward edges. Yeah. So both SDV and SNP are taken as feature vectors for our machine learning models. We utilize locality and neighborhood context, which can provide better location identification. Our data set, we use a data set of 15 million pages over, it's around 38.93% out of 38 million pages. They have distinct location information. 2.4 million are US pages and 12 million are non-US pages. California accounts for 20% of all US pages, and half of the pages, for around 50%, are located in top 5 states: California, New York, Florida, Illinois, and Texas. We map this city to corresponding states which it resides. There are actually around 30,000 cities in the US. Here's the accuracy summary. For the baseline, we use 80% as for training and 20% for testing. There are because the number of classes is rather large, random forest classifier is adopted instead of gradient boosting classifier. Yeah, so here for the baseline classifier, we use naive Bayesian, AdaBoost, and random forest. We can see that the random forest classifier is at least 20% better than the counterparts of naive Bayesian and AdaBoost. Also, the baseline used in the random forest is 10% better than the majority vote algorithm. In addition, with the addition of SNP, or the advanced algorithm also got 20% better than the baseline, which is which improves very much. So here we take a look of the accuracy detailedly by state. The results of blue shows 20% better in the advanced algorithm. We mark it as blue. So we can see the advanced algorithm, half of the states in the advanced of the advanced algorithm are 20% better. This means that combination of SDV and SMP really works. The both parts are the worst results. Um, we can see the class of New York gets worse prediction result 48%, California 53%. These two states account for most public pages. So a page has higher probability to connect with these two pages, with pages in these two states. So in addition, most states have F1 scores greater than 0.8. We take another look from the confusion matrix. Normalized confusion matrix. The green grids are the correctly identified class. The pink are the topmost misidentified class, and the orange grids are the second highest, and the yellow are third. In a baseline, we have these findings. Many color grids come from these 30 states: California, New York, and Florida. These top 30 states account for most pages on Facebook, and hence they also have a higher tendency to connect with other pages. Yeah. So it will result in the misidentified classes. Also, we can find OT other regions as another primary source of color grids. Because only due to we only use hop distance in the baseline, a page is more likely to have multiple minimum hop distance without leaning toward a specific state class and thus be classified as OT. And third finding is that geographically neighboring states could skew identification, like Connecticut and Massachusetts. For the advanced algorithm, we found that most color grids come from the top 5 page populous states like California, New York, Florida, Illinois, and Texas. This is a side effect of incorporating neighbor pages probability, because these states have higher age connections than the others. And we found that far fewer color grids also with lower percentage values in OT. This means that we have a much more effective classifier than the baseline. Also, we can find that since since most orange and yellow grids have percentage values lower than 2%, here we care only about the red grids outside of top 5 page populous states. We can find these strong ties like Delaware and Pennsylvania, NH and MA, WV and NC, also Wyoming, WY and Colorado. The next part I will talk about global page detection. The motivation is localization. Locality differentiation will facilitate subtle division of information for different audience. Regional analysis in social research also want to remove global pages to do a local base research. Also, understanding location of target audience is very important in marketing strategy. For example, BMW has distinct advertisement based on elements such as geography, culture, and language. CBS broadcasts different messages to different groups by dividing its viewing audience into separate groups, also based on geographic data. So we found that these global pages have connection with multiple regions and do not lean toward a specific region. There are mainly two kinds: international and also interstate. So we define global pages. Pages belong to a page set P, and also they have delta J greater than the threshold of global page. So delta j is 1 if delta pj is smaller than the minimum of delta pk plus error distance, where delta pk is the summation of wi times dpi. dpi is the distance between page p and class I, and it's zero otherwise. So our detection flow is we first see if this page belong to US or not. If no, then we label it as OT. If yes, we put it into classifier, and the classifier would tell us it's either local state or OT. If it's other region or other countries, we see it as global pages. So global pages are those within US but have characteristic either international or interstate. International are those similar to pages in other countries, and interstate do not link toward a specific state. So our experiment setup for minimum hop distance, mHop is a minimum hop distance of both inward hop distance and also outward hop distance of a page. So local pages in US show local tendencies, so we choose pages with number of minimum hop smaller than number of local threshold. For others, we want those pages with global tendency, so we choose those pages with number of mHop greater than number of global threshold. These are the most common global pages of international pages are those closely linked with Middle East contents. For example, like the left figure is an international page located in New York. It's mostly Middle East contents. Also, the other part is the interstate global page. They are mainly commercial oriented, which intend to connect multiple regions. So as the right figures, it's a Tabasco sauce page located in Louisiana. It's commercially oriented. So we look the global page distribution by state. If we look by state, it's 1% on average, and not surprisingly, New York has highest global page ratio, around 5%. This is consistent with our image that New York is a global melting pot. California is the other one, which higher than 2%, which shows its global diversity. We see from the demographics point of view, thus we rank states by number of global pages over population density. In this rank, Alaska ranks the first, which manifests its endeavor in travel promotion. And the following are the most popular states: California, New York, and Texas. The last part I would talk about future work. The first direction is user location attribute prediction. The motivation is that although there are many previous work on the text-based prediction, it's very easily fooled because malicious users and thus would be vulnerable. So I like to build users location attribute prediction model by features that are hard to fake. So like users activities on public pages, also activity time, language habits. Challenges are it would be multiple languages, and also people in the same ethnic group may have similar behaviors. Second, I like to do analysis on global pages versus local pages. The motivation is localization is an intrinsic property which may affect pages' characteristics. Thus, I expect that I can explore community difference between global pages and local pages. Also, I like to see how this distinction would affect users' characteristics, like number of comments and reactions, frequency of comments, also nationality, demographics. The last part, I like to work on adversarial page injection analysis, like the right figure, Heart of Texas. It's the most popular Texas secession page on Facebook, but it was found to be a Russian fraud. So it also reveals that machine learning algorithm can be easily fooled by this kind of malicious attacks. Yeah, it's a machine learning deficiency. So the challenge is how do we detect data manipulation in different strategies, because these different strategy may have different characteristics. So the other one is how challenge is how do we collect data for evaluation. So my research schedule, first part just started, so it may take 3 to 6 months, and the analysis on global versus local is 50% done. So it may take around 3 months, and the last part is not yet started, so it may take half a year to one. Until now, I have 3 publications to working with Professor Barney, so I'd like to thank him for the precious advice. Thank you. Any question?